Yeah, I'm not intend. I didn't intend having subscribers. Of course, it is the number of subscribers very few, but I didn't. mm, oh, I hope that my video would be help them. Maybe there's no the future. I don't know. I will be still I will do still upload other video after this class. Okay. Okay, then start again. In previous chapter we talked about knowledge rank and knowledge, and actually there was one more theorem, but I will skip it because I don't think it is important, and it is just considering the nullity and as nullity as a linear system, the solution space of the homogeneous linear system, and it is very makes sense theorem. So I will skip that theorem and let's enter the next chapter, eigenvalues and eigenvectors. In this section, we will define, of course, what is eigenvalues and what is eigenvectors, and these are very useful to understand a matrix or linear transformation or some for any object in linear system, linear algebra. So why we need to consider this notion is that, in my opinion, it is to analogize a large matrix, then it is hard to calculate every time the matrix, because the matrix is too large to calculate it. So in this sense, we might need some decomposition of matrix. If you have a large matrix in a computer or in your hand or in some sense, to calculate the matrix A, we will divide this space like a small space. If we calculate from this area and we study this area, and actually we will not study another area because linear a matrix, if you see a matrix as a linear system, then and then if you see the matrix as a given vector, a given basis, all of the bases b1 to bn and b1 to bn, then when you see the space of here b1 to b I1, b1 to bi1, then the space spanned by b1 to bi1 will be same. If you define this w1 and w1, then the space is same of the column space and the row space. So in this sense, when you see a matrix A, it can be considered the linear operator from V to V if the whole space was V. And by restricting this operator to W to W, you can get a smaller matrix from A. And if you define W2 and Wm, by studying W1, the operator from W1 to Wm, you can understand the whole matrix A. It is a basic notion of decomposition of linear system or linear operator or other mathematical objects. Many mathematicians are working in the analysis. So eigenvalue and eigenvectors also work like this way. So why it works like that is it is hard to convey to understand why it works like that, but we see only one matrix A as a number, so we eventually want to make the linear equation of here. This lambda is a real number R in R. Then actually two thing is not same object, but it will be in the if A was on linear operator from V to V, then it will be in V, and lambda x will be also V. So we can compare two vectors as a vector, and if it is same, then for these vectors x, we will restrict this subvector space like a subvector space by gathering these x who satisfies that equation. So naturally we can define the eigenvector if A is on n times n matrix, because the domain space would be same to the dimension of column space, because to compare the result of A of x and just scalar multiplication of x, lambda x want to be in the codomain space. So we will consider square matrix A, and then the vector x in R to the n is coded on eigenvector of A if there is a scalar lambda Ax is equal to lambda x. And I write like this, and the scalar lambda is coded to be on eigenvalues is just coded on eigenvalue. Actually, we do not have only one lambda. There are some possibility. There are possibility to have several lambdas, but these all scalars lambda will be coded on eigenvalue of A. Let me give an example. If you consider the vector x 1, 2 is will be an eigenvalue eigenvector of the given matrix A 3 A 0 1. And it is coded corresponding to lambda. So when you consider an eigenvector, that means you have an eigenvalues of the matrix, because it will be a pair lambda and x. If you change the lambda, then the value of x will be changed and composite and so on. So the eigenvalues was 3. It's easy to check lambda equals 3 is eigenvalue, because if you calculate ax, then 3a 0 minus 1 1 2 is equal to 3 6, and it is same to 3 multiplication 1 to 2. So it is 3x, and we define the lambda is 3. So lambda would be an eigenvalue, and from here the vector x would be eigenvector. Corresponding to lambda equals 3. This is the notion of eigenvalues and eigenvector. And when you consider this equation ax equal lambda x, it is exactly same the equation. I will write x as a board notation. Same, the identity matrix multiplication x is also x. So although we write like this, it is same equation, then we can calculate it as from the distribute rule by calculating a minus lambda I. It will be 0, or it is saying the lambda I minus a x equals 0. It's also same, but I will usually use this notation. And if you see the textbook, then in the textbook they are using the later one, but I prefer the former one. So it is same, just all notion is same. So I will mention. Let's consider it. And it is very useful to calculate the eigenvalue and eigenvectors to get them. So let's define what is the equation. It is a linear equation, so we can say it. We can see it as a equation, but before that, let me consider one more thing. If it has infinitely many vectors x as a solution, that means the nullity of this space should have more than 0 dimension, and we want this situation because finally we want to get the eigenvalues and eigenvectors, and to calculate them we are using this equation. But if there is no the solution of this homogeneous equation, then that means there is no eigenvalues and eigenvectors. And if there is only one solution, then the exact solution will be only 0 vector. And we do not want to find 0 vector. We want to. It is not interesting solution, and we want to find some eigenvector like this non-zero vector. So we will consider it has positive nullity, and that means the nullity is not. That means the determinant of a minus lambda I should be non-zero. Should be 0 to have nullity. So if A is on n times n matrix, then lambda is an eigenvalue, means the equation determinant a minus lambda I equals 0, and equivalently determinant lambda I minus A is equal to 0. Thus it has a sign issue, but it has equal to 0, then it will make sense. One example. We don't need to write two things, because if it is 0, then it will be 0 because it is going to minus determinant of a minus lambda I. And so I said that I will use this notation instead of this. So after this class we will use only this equation like this. And it is the definition. This equation is called the characteristic equation of A. And by calculating the solution of the characteristic equation of A, you can get the eigenvalue lambda of A. And now let's see the previous example. We saw that lambda equals 3 was an eigenvalue. And to calculate it, let's see the equation A minus lambda I is determinant. It means we will calculate 3 minus lambda, 0, 8, minus 1 minus lambda, and it is exactly the same the equation here, and from here we can get the solution is lambda equals 3 and minus 1. So we can get the eigenvalue of A. So in this sense, then the important thing is the polynomial for lambda in this equation. So this polynomial is called the characteristic polynomial. If we denote it is P of lambda, then P of lambda is called the characteristic polynomial of A, and the dimension is the degree of the polynomial is same to the dimension of column, the number of column or the number of rows. So in this example case, you can see it was triangle matrix, and actually we will calculate the determinants of A minus lambda I, then the triangle matrix like A11, A12, A1n, A22, ANN, if you consider it, and another is 0. If you calculate the determinant of the matrix minus lambda I, would be the multiplication of the main diagonal elements. That means A11 minus lambda, A22 minus lambda, ANN minus lambda. And then the in this sense, the eigenvalue also we can calculate it. This is a characteristic polynomial, and if you get the solution of characteristic equation, then lambda would be A11, A22, ANN. So the next theorem is saying the notion of here. If A is n times n triangular matrix, such as upper triangular or lower triangular, and diagonal matrix is also triangular matrix. So these are the example of triangular matrix. A is an n by n triangular matrix. Then the eigenvalues of A are the entries on the main diagonal. Of A. So as you can see, the matrix A here, the matrix A was 3, A, 0, minus 1, and so the eigenvalue was 3 and minus 1. This was a good example. And so let's summarize the notion of eigenvalue for an n by n matrix A. The following equivalence, I will give an equivalence theorem. Lambda is an eigenvalue of A. That means it satisfied the equations. So it is same to lambda is a solution of the characteristic equation. It was determinant A minus lambda I equals 0. Then lambda what would be the eigenvalue, and it was it has if and only property, and it is saying that the system of equations A minus lambda I multiple x equals 0 has non-trivial solution. It was the notion when we firstly mentioned to get effective eigenvalue, non-zero vectors. The linear system should have non-zero vector. Should have non-zero vector as a solution of this linear system, and this is also same to having eigenvalues. And it is same to that there is non-zero vectors x. Satisfying the first linear system here. We start from here, and this 4 notion is all same. And firstly, I mentioned that we will find this all solution x for an eigenvalue lambda, because we want to divide the space, the large space V to a small space W1. And now the one eigenvalue can give one vector space because the x could be gathered from the homogeneous linear system, and we already learned that the solution sets of a homogeneous equation will be a vector space. So if you gather the solution set in here, then it will be a vector space. And the vector space is called the eigenspace. So let's define it. Let A be an n by n matrix, and let lambda be eigenvalue of A, and the linear system, the solution space of linear system. Linear system A minus lambda I x equal 0 is called the eigenspace. Of A corresponding to lambda. So it means it's same to the meaning that the space of A minus lambda I, it would be the eigenspace of lambda corresponding to lambda of A. So let's see an example. If you see a matrix minus 1, 2, 3, 0, and then by calculating row echelon form, you can get no row echelon form. Just calculate. I will start again. Let's calculate the characteristic equation. A minus lambda I is determinant. It is minus 1 minus lambda 3, 2 minus lambda, and the characteristic equation is this is equal to 0, and it is minus 1 minus lambda minus 6, then lambda square plus lambda minus 6 is equal to lambda minus 2, lambda minus 3, lambda plus 3. You're right. Minus 6, 1, okay. So we can obtain the eigenvalues. Lambda is equal to 2 and lambda is equal to minus 3. And to find the eigenspace for lambda is equal to 2, we should find the null space of A minus lambda I here when lambda equals 2. The null space of A minus 2 lambda is will be get from to calculate this linear system, and then let's separate it. Minus 6, 6, 6, 6 by multiplying 2 and by multiplying 3 respectively, it will get the matrix of the solution. Oh, wait. From, oh wait, I think something wrong. -2, here's -2. Yeah, then we don't need to calculate it. We will get this equation, and it will give one leading term and one free term. So by giving a parameter t, it will give the solution set would be t, t in R32, and it is the eigenspace of A corresponding to lambda is equal to 2. And if you calculate -3, then that means the eigenspace of A corresponding to -3 is the null space of here. And let's calculate it. The remains. The null space of A plus 3I can be get from the calculating the solution -3 +3 2 3 2 3, and the null space then will come from the solution set over here, and it has one leading term and one free parameter. So the eigenspace for eigenspace corresponding to -3 is the solution set of t 2t minus 3t. So if you calculate it, it will give the solution. And so it is the eigenspace, which is the eigenspace of A corresponding to -3. So we found all eigenspaces for about A. And let's see. Oh, one more theorem. I erase here. A square matrix A is invertible means matrix A is invertible means the eigenvalue is lambda is equal to 0 is not an eigenvalue of A. From the I erased it. If lambda become an eigenvalue of A, it should be satisfied with this equation, and equivalently we saw that the characteristic equation would be 0, and so if lambda is 0, then that means determinant A is 0 is equal to lambda is equal to 0 would be the eigenvalue of A. So so if A is invertible, would be the converse notion, but invertible, because determinant of A is 0 means A is not invertible. So if a square matrix A is invertible, that is equal to lambda is 0, is not an eigenvalue. If A is not invertible, then lambda is equal 0 should be should be 0. At least one eigenvalue. Yeah. Vector X. Yeah. If you consider 0 vector, then in this sense, we will not say lambda is eigenvalue. We started from this equation, but every matrix A, you can get x equals 0 as a solution. And then if you bring x equals 0 vector, then for every lambda, scalar lambda, satisfies the equation for 0 vector x. So we will consider eigenvalue lambda. Lambda would be an eigenvalue of A, means there is a non-zero vector x, so that satisfies that. Yeah, we do not know this will be eigenvalue or not. And the final theorem of today. From this text, I will add one more. I think it is also the same. We are seeing the matrix A is invertible, and its equivalent relations. It is lambda is 0 is not an eigenvalue of A. It is also equivalent property. Okay, here is done.